I am Vineeta Pal, and today we will be studying about the velocity distribution in open channel. Since previously we have studied about the introduction portion of open channel, that is what is open channel, its classification based on different categories, its parameters involved in it. Now we will be going into depth of velocity distribution into it. We can see that this is the open channel, right? And this is the free surface. So you can see at the boundaries, velocity distribution is at velocity is equivalent to 0. Above the bed surface, it is termed to as minimum velocity, and below the free surface, depth up to free surface, it is given as V max. We can see that velocity distribution or contouring of velocity, similar patterns of velocity we can see. At the boundaries, we can consider it as velocity will be 0, because at the boundary the flow will be connected to 0. As it is hitting the boundary, the velocity the very next moment the velocity will be coming to 0, and again with the hit of it, it will possessing certain velocity and it will be trying to have certain minimum velocity it's being having to it, and we can term it to as V minimum. And V maximum can be calculated, and it has been calculated in several studies by different hydraulicians as the depth after certain depth from free surface we get or we achieve maximum velocity, and that particular calculation is being done or data analysis has been done, and they have termed as V max is found to be 0.2 of y. Any channel having a depth of y, its 0.2 depth, if we have covered its 0.2 depth, we will be achieving V max of it. And if we are moving towards the downward and we are covering about the 80% of the total velocity, total depth, I am sorry, we can achieve V minimum, that is 0.8 of y after covering, suppose if this is y, if this channel is having y as a depth, then we can achieve maximum velocity after covering its 20% of total depth, 20% of this depth, and minimum will be around 80%. And here we can see V average was found to be at 0.6 of y. This was found by data analysis, but what you can do, this is minimum, this is maximum. If we take the direct average of it, we can get the average velocity, or you can say this value can be helpful. V average can also be attained with the help of V minimum, that is this one, plus V maximum divided by 2. Next one. Now next is Isovel. What is this term? The term Isovel can be defined it to as all the contours having same velocity or equal velocity. All the contours having equal velocity are known as Isovels. And the dip of this maximum velocity, up to where this maximum velocity will be moving or will be depending upon the depth aspect ratio, that is the ratio of its depth to the width of channel. Third one, we can see a velocity distribution can also be categorized depending upon the geometry of the channel, like if it is rectangular, trapezoidal, triangular and circular. In rectangular channel, we can see that in all these geometries, all these different cross section, what we can do, we can draw a perpendicular line, perpendicular axis, or we can divide according to the symmetry, right, or we can divide according to the symmetry any channel. this was rectangular channel. Rectangular channel we have divided symmetrically, and here we can see this will be the maximum velocity and this will be the minimum velocity, and you can see this is the graph we are achieving. It won't be 0 over here, it will be having a velocity less than the velocity we have achieved over here. Then we can termed as V max over here and V minimum over here. Coming to trapezoidal section, we have divided the geometry upon the symmetrical axis. Here it is V max, again here it is V minimum. This graph is attained. This is similar to what? Similar to that particular section we have studied in fluid mechanics and pipe flow. Similar to it, not exactly to it. We can see we have divided this, and what contours we are getting. This will be minimum since this particular section will be keep on changing, right. Here it can achieve maximum velocity and here as minimum, or you can say at the center it will be having V max. Coming to the triangular section, again at the top you can see it is having maximum velocity, and at bottom it is not having minimum. In fact, it is having negligible velocity, but we cannot say it is 0 because it keeps on moving at certain velocity, it keeps on flowing. This was the contouring of velocity distribution in triangular section. This is based on the geometry of the channel. Now, we can see for the calculation of average velocity, it is similar what we have done in the previous one. Here we have studied in general cross section of any channel having depth of y. We have studied that average velocity can be calculated with the help of, this is V max and this is V minimum. Average of both will be giving the average velocity of the channel, where V2 I have already told you in the previous slide, velocity at depth of 0.2 or 20% of the depth. H is nothing but depth of channel. You can see this is rectangular channel, this is the depth, that is H, or you can say y accordingly, and here you can say 0.6, that particular study about the hydrolysis 0.6 at after covering the 60% of the depth of any channel, we can attain a velocity as average velocity. Now, we can say this was about the empirical relationship, or it is based on the case study. This formula is driven from case study. Now, we can derive the equation for calculating average velocity. For average velocity, let us consider this is an arbitrary area, capital A. We can consider one elementarily portion dA, one elementarily portion dA, and here we can say, since we know that discharge or rate of flow is equivalent to the product of area, cross sectional area into the velocity of it, we can say discharge dq, dq of what? This elementarily area, or the discharge passing through this particular small elemental area will be equivalent to what? Elementarily area delta A or dA into velocity small v of this elemental area. This is dq. Similar thing is written over here. dq is nothing but product of velocity into this area of this element. What if we are supposed to have all this, the rate of flow through this whole surface, full surface, what we can do? We can integrate it. Integrating it, what we are getting? dq into q, capital Q. Capital Q it as, or you can say integrating it, it is giving it as capital Q is equivalent to integration of this, right? And then capital Q, we know that capital Q is nothing but A into V. A into V is equivalent to what? Integration of delta A into small v, or you can say V is nothing but this particular A will be shifting over here, or we have got equation for calculating average velocity in any channel can be V is equivalent to 1 by A V into d, integration of V into dA. This is the equation for calculating average velocity in any channel. Now, coming to the section, since we are already aware that the velocity distribution is not uniform, it keeps on changing, and during a certain span of time or during a span of length of the coverage of that particular channel, there are certain correction factors or which takes us to the accuracy or approximately nearer value of the velocity distribution. Since velocity is directly proportional to is directly involved in energy and momentum calculation, we can say that we have one energy coefficient and momentum coefficient. Repeat, after studying the equation for calculating average velocity in open channel, we need to focus what are the factors affecting the velocity distribution in channel, like energy coefficient factor and momentum coefficient factor. Reason being, velocity is directly connected to the energy equation and momentum equation. So, first basically moving towards the equation of energy coefficient, and energy coefficient is represented by alpha is represented by alpha. What we can see, we can calculate alpha or the correction factor, actually difference between the actual velocity due to the kinetic energy involved into it. We can say that, let us consider a cross sectional area A of any channel. Let us see, capital A is whole cross sectional area, right, and capital V is average velocity of this channel, small w is the specific weight, right. To calculate the energy correction factor, what we can do, we can calculate it with the help of elemental area. Let us suppose this is the elemental area dA, area having velocity small v, now we can say kinetic energy passing through this particular area delta A will be, kinetic energy is nothing but half into mass into square of velocity, half. Now, how about the mass? Mass entering into this elemental portion, it will be nothing but weight by g into the small v square. Coming to weight, how we are going to calculate the weight? With the help of specific weight, what we can do it, half weight can be written with the help of specific weight as specific weight into dA into V. This will be weight, if we are going to divide it by g, it is mass, and again square of velocity, or you can say kinetic energy through this elemental area will be nothing but 1 by 2 W by G, what it is, V cube, small v cube into dA. This was through this elemental area. What if we are supposed to calculate the kinetic energy for this whole section? Summation of all these kinetic energies will be giving you total energy. So, what we can do, total energy, total kinetic energy will be what? Summation of 1 by 2 specific weight by G V cube into dA. This is equation number 1. This we have calculated the total energy with the help of integration or having summation of all these such elemental portion throughout this area. Now, what we can do, if we are considering A as area, V as velocity, total kinetic energy as a whole area, capital A with velocity V and having correction factor alpha, corrected energy factor, it will be nothing but alpha half, mass can be written as specific weight into A, capital A, into V, capital V, mass, for making it as mass, divide by G, and velocity V square. Similar things are alpha 1 by 2 specific weight by G, capital A, and this will be capital V cube. This is equation number 2. This kinetic energy with corrected energy factor we have found out as a whole body, surface we have considered, and this one through the summation. So, both should be equal to it. Equating equation 1 and 2, what we are getting, this is equation number 1, this is equation number 2. What we are getting, alpha, what it is, alpha 1 by 2 specific weight by G, capital A, capital V cube is equivalent to, this is equation number 2, what we have got as equation number 1, summation of 1 by 2, similar things were there, but only the section was, it was elementary due to the summation. So, we can write 1 by 2, summation of 1 by 2 specific weight by this, and instead of capital A as a whole, we are going to do summation of elemental area into the velocity of that elemental portion. You can see this value and this value will get cancelled, this value and this value will get cancelled. What you are getting it as, alpha is nothing but summation of V cube dA by this one V cube into A, or you can say alpha is nothing but integration of small v cube into dA upon V into A. This is the energy correction factor alpha, and we can calculate the value of alpha by this formula. Now, moving towards momentum correction factor. For momentum correction factor, we can see that momentum is nothing but, all the sections will be same. This is nothing but an area capital A having velocity capital V. Let us consider again one elemental thing, that is dA, and it is having a velocity small v. Now, we need to calculate about the momentum. Momentum formula is as m into v. Let us suppose momentum in this particular area dA is m into v, where m can be similar to that of how we have calculated the m, value of m, mass, this value, right, specific weight, mass can be written as specific weight delta A into V by G. This will be mass into small v, m into v. M is written as weight by G is m, and here V is V. Now, you can say momentum through this elemental portion, momentum through this elemental portion is nothing but specific weight by G delta A and V square. For calculating the momentum through this whole area, we can do the summation of all this momentum, elemental momentum of all this section can be giving the momentum of whole area, and this is termed as equation 1. Let us consider, since we have already assumed this whole area is having capital A as velocity and A as area and capital V as velocity. So, what we can do if it is having, and what we are terming it momentum correction factor as beta. Now, momentum by whole area. Will be beta m. For m is what? M into V. M is what? Specific weight by G. Specific weight by G. Let me erase this section. Into what? Delta A into V was for A into V. For the whole section, it will be capital A into V, capital A into V, and again V. For V, it will be capital V. Or you can say it is, corrected one is beta into specific weight by G capital A dot V square. This is equation number 2. Equating equation 1 and 2. What we are getting? Equating equation 1 and 2, we are getting beta is nothing but integration of V square dA by V square into capital A. This is the equation for calculating momentum correction factor represented by beta, and here we can see that we have studied about the velocity distribution in an open channel flow, and what all we have covered? We have covered the velocity, average velocity, maximum velocity, minimum velocity. Next we have covered alpha, that is energy coefficient factor, energy constant, and beta as momentum. In next slide, we will be studying about the specific energy curve and concept of critical flow and critical depth. Thank you.